Hello, it's your favorite teacher, and I'm here to do some problems with my favorite class. Starting with number 2, this is from the extra review worksheet. So we've been working with this. Like I said, it's a good representation of what could be on your test. So that's what I'm going to go off of. This is a problem we did not do in class yesterday. It is number 2. It is a graphing problem, and it's specifically a decay problem. And I knew it was a decay problem because it's 1/2 to the x. So when this inside the parentheses part is a fraction that's smaller than 1, okay, it's going to be decay. So I know you guys are worried that graphing without the graphing calculator is going to be really hard, but I'm going to try to make it very easy for you. Start with the asymptote. The asymptote is always going to be this number that is at the end of the equation. So this plus 1 is going to be your asymptote. So that's going to be at y equals 1. Alright, so there's a reason why it's y equals, and that's because this is an exponential problem. Yesterday I put notes on your sheet that talked about when it's a horizontal asymptote versus when it's a vertical asymptote. Vertical is for logs, horizontal is for exponential, and so our asymptote equation is at y equals 1, which means at positive 1, I'm going to have a nice horizontal asymptote. Okay? Alright, moving on. Guys, do not make this hard for yourself. Just plug in. I'm picking my values as -1, 0, 1, and 2, and I'm literally just going to use my calculator to do parentheses, 1/2, you can even do 0.5 to the negative first and then plus 1. You'll have a scientific calculator to do that. Okay, and when you do this in your calculator, 1/2 to the negative first is actually 2 plus 1 is 3. So you should be able just to plug that into your calculator and make it much easier for yourself. Doesn't matter if you have a graphing calculator. Just do 0.5 to the 0 plus 1. That's 1 plus 1, that's 2. Next one, 1/2 to the first, plus 1. It's going to be 1.5. And finally, 1/2 to the second, plus 1. Put that into your calculator. That's going to be 1.25. Alright, that's it. So now just plot those points. -1, 3 is up here. 0, 2, right there. 1, 1.5, I mean that's just kind of approximate, and 2, 1.25, even closer. So I'm going to zoom in. Remember with the shape of an exponential. Now this one's decay, so it's going down. That's our general shape. And the domain, okay, so for all exponential problems, decay or growth, it doesn't matter. The domain is -infinity to positive infinity. And the range is bottoms up, which is going to be the asymptote to infinity. So this one's going to be 1 to infinity. This is a decay problem. Alright, so we're going to move on. That was number 2. Let's go to the next problem, the log graph. This is number 4, because we already did number 3. Alright, now this one, a little bit different. I like to start by circling up. So circle up. When you do that, you have 4 to the y equals x minus 1, because it has to equal the whole parentheses. Now this one's a little bit harder, because you cannot start plugging in until you get the x by itself. So our equation is actually 4 to the y plus 1 equals x. This time we choose numbers for y instead of for x, and the reason is because it's an inverse, it's the log. Same numbers, -1, 0, 1, and 2. And now I'm just going to plug in these numbers into the y. So 4 to the negative first plus 1. That's 1.25. Next one, 4 to the 0 plus 1. That's 2. Again, you can just use your calculator for this. 4 to the first plus 1. That's 4 plus 1, which is 5. And finally, 4 squared plus 1 would be 17. 4 squared is 16 plus 1 is 17. That one won't fit on the graph. That's fine. Okay, asymptote for log functions. Whatever you're taking the log of, okay, this x minus 1 tells me, if I set it equal to 0, where my asymptote is going to be. So you want to get x by itself. So it's a vertical asymptote. That's something to memorize at x equals 1. Usually for log functions, guys, it'll be at 0. The only time it's not at 0 is if you're taking the log of a quantity. Okay? Alright, so just if you're taking the log of a quantity, like this. Okay, almost there. Domain and range. The domain for this is going to be the vertical asymptote to infinity. So 1 to infinity. And the range for all log functions is negative infinity to positive infinity. Okay, and for log functions, you can ignore growth or decay. All right, guys, I haven't even graphed this, and I was able to do the asymptotes and everything, because I'm pretty good at this, and so are you. So positive 1 is the vertical asymptote, and let's just plot these points, 1.25, negative 1. That's like right there. 2, 0. That's like right here. And then it was 5, 1. And that's all you can fit. So there, and don't forget, guys, the log function goes down forever. So there we have it. It's just the log function shifted right 1. And we're going to move on. Next up is a condensing problem, So when you condense, you always start by bringing up your exponents. Bring them up. So here I have the natural log of 9 to the 1/2. We're going to simplify this in a minute. All right, this is a weird one. So we have now natural log of 3y squared, okay, and minus, we have natural log of 8x to the 6th to the 1/3. Okay, all right, so now we got to simplify this. All right, starting with this natural log of 9 to the 1/2. 9 to the 1/2 is 3. So we have the natural log of 3. Plus, guys, I'm going to square the 3 and square the y. So plus natural log of 9y to the 2nd. All right, next I'm going to do 8 to the 1/3. Careful. 8 to the 1/3 is the cube root of 8, which is 2. So really this is minus the natural log of 2. And then 6 times 1/3 is 2. So it's really 2x squared. Okay, now we just have to condense. So because of this addition sign right here, okay, that means that I'm multiplying. Multiplying means both of these are going to go on the top. So I'm going to have one big natural log. 3 times 9y squared goes on the top, and wherever there's a minus, it goes on the bottom. And that's over 2x squared. One more time to simplify. Natural log 3 times 9 is 27. Y squared all over 2x squared. That's the answer. All right, let's go on. Next one's a solving problem. Okay, so this is number 29 from the review. So, guys, we have to condense to start. So left-hand side, there's more than one log. On the same side, that always is going to mean condense. So natural log, since it's addition, I have to multiply. So I'm going to write it as 5x equals natural log of x squared minus 36. Once you have log equals log, or natural log equals natural log, you just have to set whatever you're taking the natural log of equal. So it's kind of like these natural logs kind of cancel. And we have 5x is equal to x squared minus 36. All right, guys, so here, let's subtract over the 5x. It won't combine, so we have to factor this. X squared minus 5x minus 36. Factors to 9 and 4. X minus 9, x plus 4 equals 0. So we get two answers. X equals 9, x equals negative 4. However, the negative 4 answer won't work because I can't take the log or natural log of a negative. So the answer for this one is just 9. Nice. We're going on. Ooh, this guy. All right, we did one of these in class. This is the hardest type, in my opinion, but you guys can do it. It just takes practice, so just practice. I cannot rewrite 7 and 3 to have the same base. So right away, I'm going to log both sides. Guys, you could log or you can natural log. I like natural log only because it's the same every time then. Next step, take your exponents and drop them. Drop it and drop it. Here we have a 5x natural log of 7 equals, parentheses, 2x minus 9 natural log of 3. We have to distribute the natural log of 3. So I have 5x natural log of 7 equals 2x natural log of 3 minus 9 natural log of 3. Next step, get the x's together. So I'm going to subtract this one over. I'm going to have a 5x natural log of 7 minus 2x natural log of 3 equals negative 9 natural log of 3. Alright guys, next step, factor out the x. Both of these guys have an x in common. So I have x parentheses 5 natural log of 7 minus 2 natural log of 3. Okay, equals negative 9 natural log of 3. Wow, so close. This is record timing. The next step is to get the x by itself, so I have to divide both sides by this whole quantity. And I'm just going to kind of take a shortcut and write out the answer. It's got to be a negative 9 natural log of 3 all over the 5 natural log of 7 minus 2 natural log of 3. And that's the exact answer. That's it. Now, when you plug this into your calculator, you want to be very careful and use parentheses around the entire denominator. Okay? But that's it, guys. That's really all it is. Okay, it got a little weird there. There we go. Here's all of the work together. Practice this type of problem. And I'm going to move on. Okay, so I'm just going to do 2 word problems and we'll call it quits on the video. This one's number 35 on the extra review sheet. So it says in 1950, the population of a city was 120,000. Since then, the population has increased by exactly 1.5% per year. Write an exponential growth equation giving the population P T years after 1950. Okay, so a couple things, guys. There's a lot of formulas here. And the biggest thing to remember, okay, is that unless it's talking about finances and compounding, okay, if it's talking about compounding, then you're going to either use the formula with the n in it, or you're going to use the formula A equals PE to the RT if that's compounded continuously. Otherwise, you're going to use one of these formulas. A equals little a, parentheses 1 plus R to the T, or you're going to use A equals little a, parentheses 1 minus R to the T. So the plus R is for decay and the minus R is for growth. So for this problem, we're increasing, like I said. So we are going to get rid of the decay problem and we're going to use the formula for growth. So for population problems and literally anything that is not involving money, this is the formula we're going to use. All right, so a couple things to remember. R is our rate. Little a is the beginning amount. So the little a is the beginning population, which we said was 120,000. Okay, the R is the rate, and it's increasing at 1.5%, which is 0.015 as a decimal. Remember, 1.5%, if you move the decimal over 2 spots and fill in a 0, then you get 0.015, okay? So that's how I got the rate. I don't know the time because it says in terms of time, so we're just going to leave it as a T. All right, and then the overall population is what we're going to set this equal to. So the population is P, and the population equals little a parentheses 1 plus r to the t. Because it's increasing, so I'm using that plus sign. All right, and so now I'm just going to fill in everything I know. P equals 120,000, which is the starting amount, 1 plus 0.015 to the t. And I'm just going to combine the inside parentheses part, and that's going to be my answer. Oops. So P equals 120,000, parentheses 1.015 to the t. There's the equation. So now I'm going to use that equation. It says if the population continues to grow at the rate, what will the population be in 2010? Okay, so now I'm looking for when the time is 2010. So in 2010, how many years have passed since 1950? All right, so that's going to be 60 years. So 60 years, t equals 60 because it's 60 years past 1950. So the t is 60. Literally just plug that in, and you're going to use your calculator. So we're going to plug in our formula. The population is going to equal 120,000 times 1.015 raised to the 60th. Guys, type that into your calculator exactly as you see it. And when you do that, you get approximately 29,000. I lied. 293,000. 186.3. And since you can't have 0.3 of a person, I'm just going to round it to the nearest whole person, and that's here. Okay, so it is increasing. It started at 120,000. This is 60 years later, so it makes sense that it's more than doubled. So 293,186. All right, last one. In what year will the population be 400,000? So now I know, okay, the P is 400,000. I'm looking for T. All right, so again, my formula is P equals 120,000, 1.015 to the T. So I'm plugging in for P the 400,000. Okay, guys, so the first thing to solve is to divide both sides by this 120,000. And that comes out to be, I'm going to leave it as a fraction, so it's 10/3 equals 1.015 to the t. Now, since t is in the exponent, the only way to solve this is to natural log both sides. So I have the natural log, or you could just do the regular log. It doesn't matter. Natural log of 10/3 is equal to, drop down the exponent, so t times the natural log of 1.015, and then just divide both sides by the natural log of 1.015. Okay, so once we type in our calculator, this part right here, okay, my natural logs cancel on this side, and I get 80.86 equals t. So approximately 80.86 years. So about 81 years. Well, okay. This is weird. So here's the whole problem, if I can somehow zoom all of this in. There we go. There it is. Yay. All right, moving on. That was long. One more. Last one. Okay, in 1996, the tuition for 1 year at the university, at the best university ever, Michigan, okay, Driscoll/Young, was $8,345. Throughout the next several years, the tuition will increase by 5.67%. Okay, it doesn't say anything about being compounded, so I'm going to stick with my original equation. We are increasing, so it's 1 plus r to the t again. Okay, guys, so beginning tuition was $8,345. Rate is 5.67. So I'm just going to go right to the equation to save time. We have A equals the beginning amount. Remember, the beginning amount is 8,345 times 1 plus the rate, which is 0.0567 to the t. Combine, and we got our equation. So that's A equals 8,345 1.0567 to the t. And now it says if you start there in the fall of 2016, how much would your tuition be? So we have to figure out how many years have passed since the beginning. And it started calculating this in 96. So 96 to 2006 is 10 years and another 10 years, so 20 years has passed. So literally just plug in. A equals 8,345 times 1.0567 to the 20th. Plug that exactly into your calculator. And when I do that and plug it in, I get my final answer, which is $25,145.51. Wow, after 20 years, the price has definitely gone up. But still believable, in the realm of possibility. All right, guys, wow. This was long, but I've really gone through a lot of different types of examples, so go back and rewatch if I went too fast. And study. You got to study tonight. Check all your answers. Peace out.